So the work I'm going to discuss today is a part of collaboration that I have with NOAA National Severe Storms Laboratory. I just finished up a 6-month visit there. I'm going to be talking about some of the results that, from my work. And I first want to acknowledge my co-author, Lou Wicker, at NOAA National Severe Storms Lab, who invited me there and helped me with a lot of this. So this application that we're interested in is at the convective scale for weather forecasting. And this is a very challenging topic for a variety of reasons. And I'm just going to mention a few that are relevant to this particular talk, which are, the first one is whenever you have some displacement error in discrete structure in your domain, such as mesocyclone for a severe weather event or clouds themselves, you tend to have very non-Gaussian errors associated with the state variables of your system. Another is cloud processes are quite nonlinear, which makes the problem difficult. Another is that the measurements that we have often relate nonlinearly to the model state. And they're also measuring these cloud processes many times. And the storm environment interacts with the environment in a nonlinear way also. So it's a complex multi-scale problem. And there's a lot of work that came out of Derek Posselt's group that uses MCMC to evaluate some of these complex error distributions. And a lot of the work I'm going to talk about is motivated by some of this. So the first thing I'm going to do is go over some kind of toy problems that illustrate these issues that I mentioned on the first slide. And the first problem I mentioned is this displacement error issue. And it's very easy to reproduce this problem just using any discrete structure that you have. And so what I'm going to do is I'm going to take an axisymmetric vortex modeled by a ranking vortex, which has a profile that looks like this, and turn that into a two-dimensional wind field, which I'm just showing here in the bottom. The hatched region is just where we have wind speeds that are greater than 15 meters per second. And I'm going to use this to create a state vector x, which has two components of wind in the x and y direction. And this is our model for our current application. And what we're going to do is see what happens when we have a position error associated with that vortex. And so all I did was I have the truth, which is this black line here, and a set of prior members. I have just 200 vortices, and there's supposed to be some samples from a prior distribution of vortices that have the same structure, but just have some position error associated with them. And we have some incomplete measurements coming from a radar, which I have in the middle of the domain. And so what I have here is a set of radial velocity measurements for a radar that's located right here that's collecting for this vortex. And so what we're going to do is go ahead and apply an ensemble Kalman filter to draw samples from a posterior distribution using Kalman filtering theory. And what you get is something that's quite suboptimal. And so what I'm showing here is the posterior members, most of which have this big axisymmetric wave number 1 or 2 component to them, which is wrong because the dynamics of our system say that we're supposed to have a set of vortices that are axisymmetric. And so this is just illustrating this problem of having a linear, applying a linear Gaussian filter for a very nonlinear problem. And the assumption that the distribution is Gaussian is good until you tend to have a position error that's comparable to or larger than the vortex size. And this is something that's well documented in some papers. Another example I want to show is what happens when you have cloud processes that you have to deal with, which are quite nonlinear, and also nonlinear measurement operators. And the best way to illustrate this is just through an idealized example that we encounter a lot for convective-scale data simulation, which is that we have a set of discrete convective cells in our domain, and we have a measurement that's coming from a reflectivity measurement for our state of interest. And we have to assimilate that to correct all of our state variables. And so for this example, I'm going to start with just a 100-member prior ensemble from a cycling data simulation experiment. And I have one radar reflectivity measurement that's located at the star. Here's just a horizontal cross-section through the domain, and here's a vertical cross-section. And so that star is being collected right along the freezing level for this storm. And so the way I like to think about this is first by just plotting what the prior samples from the joint PDF of reflectivity in those microphysics variables look like. And so on the x-axis, we're showing the reflectivity values. And so all these values is if you apply the measurement operator to each of your 100 members, you get the x value here. And on the y-axis, I'm just showing what the cloud variables we're trying to estimate look like. And so I'm showing mixing ratios of ice, rain, snow, and graupel for this application. And these distributions, of course, are very non-Gaussian. You don't need many samples to see that. And so If you can just pay attention to the ice field right here, you have, for the marginal distribution of ice, you have a distribution that's bounded at 0, and you also have something that looks quite bimodal. And so if you apply a ensemble Kalman filter to update these members with that reflectivity measurement, you get something that's quite suboptimal. You get a lot of members that are being pulled into this region here where you have low or 0 prior probability, and you have a lot of members that have 0 values as well. And you have behavior like this for a lot of these different updates. Okay, and so this brings up particle filters. And can we make them useful to solve problems such as this for applications that are quite non-Gaussian? And so what particle filters are there these Monte Carlo approaches that use samples to represent distributions, except instead of approximating Gaussian using these samples, we represent them in pretty generic ways. And so what I'm showing here is just a demonstration in which I have some bimodal prior PDF P of x here. If you draw samples from that distribution and use those samples to approximate a Gaussian, you get something that's completely the wrong result. And it has the highest probability in a region where technically the distribution has a pretty low probability. And so the method I'm going to be working with is just based on a simple idea from that's called sequential importance resampling. And so the sequential importance resampling particle filter just follows 3 steps, which I'm going to show in the next couple of slides. So first of all, we have this prior distribution P of x and some samples from it. The first step to this method is going to just assume that this prior PDF can be estimated empirically using a sum of delta functions, each one centered on those particles. The next step is to take an observation that we have with some known parametric error distribution. Here I just chose a log normal, just to show that this is a pretty general method. You could choose any distribution you want for the observation errors. And if you take the information we have about P of x, which is that it's assumed to be a sum of delta functions, and some error distribution we have for P of y given x, we can just stick them into Bayes, and the output is something that looks like this, which is that P of x given y can be approximated using a sum of delta functions. And then once you have these weights, so essentially what you have is a weight for each of these particles, which is proportional to the likelihood of the observation given each of your particles. Once you have those weights, the next step is to draw particles from the posterior by resampling based on the weights in our prior particles. So all this method is going to do is it's going to start with this prior set of particles, calculate likelihoods, and then use those likelihoods to calculate weights, and use those weights to just remove particles that have low weights or duplicate particles that have higher weights. And so in principle, it's a very simple method. And so the approach that I'm going to take to apply this method for a high-dimensional system, which requires spatial localization, just like ensemble Kalman filters, is introduced in this paper by Poterjoy 2016. And the idea is to just calculate weights for each state variable in your system, and allow these likelihoods to affect these weight calculations through some empirical localization function C, where C is a function of some localization radius and the distance between your observation and each of these state variables. So you can control the impact that those observations are going to have on your weight calculations. And so if C is equal to 1, you get the sequential importance resampling particle filter back. And if C is equal to 0, then essentially you're just going to update whatever state variable is closest to the observation. And the way I'm going to do this, the way I'm going to produce samples so that they match the properties of the posterior F given by these weights, is to process observations one at a time and merge sampled particles together with particles selected during the sequential importance resampling step. And so the advantages of this approach are that it's very inexpensive to apply for a high-dimensional system. And also, if you have if you have a large R or a radius of influence that goes to infinity, you get something that looks like the sequential importance resampling particle filter back. Disadvantage is you're applying this sampling step for each observation in your system. And so you introduce a lot of sampling error each time you do that. And so this localized particle filter was applied in 2 recent studies, one by myself and Jeff Anderson, to show that this method works well for high-dimensional geophysical flows. And here this was just using a dry coarse resolution atmospheric GCM, or a general circulation model. And a more recent paper shows that this method also works for more complex cases such as convection and WRF in the weather research and forecasting model, and even shows some benefits over ensemble Kalman filters. And this was just using 100 members. And Chris Snyder is going to show later in the week that there are a variety of other localized particle filter-based methods. And so I'm not really going to discuss this that much, but this idea is not at all new. It comes from, there are two earlier papers that use this localization ideas in a particle filter framework. And there's also many other papers that have come out over the last 2 years that apply some of these localization principles. And so with that background, we could go back and we can take this localized particle filter and apply it for those test problems that I showed earlier and see what it does. And so recall that we had this set of ranking vortices that have some position error associated with them. And the ensemble common filter produces a set of posterior vortices that has a huge wave number asymmetry associated with them. With this localized particle filter, you have a set of quasi-axisymmetric vortices with some position error. And so this is a case where we have 200 members and you're sampling from a region where you have high posterior probability using the correct vortex structure. And so it solves that position error issue because it solves the underlying problem, which is the non-Gaussian distribution that caused some of these issues for the EnKF. And in order to see some of the negative consequences of the localization, what we can do is we can reduce the ensemble size down to 80, which is what the operational global ensemble is for in the United States. And here we have to use a smaller localization radius for the local particle filter. And so you see more wiggles in each of these lines showing that you're starting to break that balance, the dynamical constraint here that the vortices are axisymmetric. But you're still doing something that's more useful from the ensemble common filter, even with 80 members. Now we can go back and revisit problems 2 and 3 for that idealized squall line case. And for the particle filter, of course, all you're doing is you're just choosing states that are closest to the observation given by the likelihood calculations that we performed. And so for this is no problem for the particle filter. But this doesn't really show the impact of localization because I'm just viewing everything in the joint observation model space for model state variables that are close to the observation. So in order to show what happens with a localized particle filter for this problem, what I'm going to do is I'm just going to keep the same values in the y-axis here for these mixing ratios, but I'm going to move the observation down 2 kilometers. So you have some physical displacement between where your observation is and where the state variables are that you wish to correct. And so now, if you apply the particle filter, all you're going to do again is you're just going to select particles that are closest to the observations. But if you apply a localized particle filter update, you get something that looks like this. And so essentially what happened was you remove some of the dependence between the reflectivity and mixing ratio values. And so you maintain the same marginal update for the reflectivity values, but you relax some of the marginal update for the mixing ratios. And so you move particles back into this other basin of high prior probability. And so you can look at this top panel right here. You're essentially just going to shift some of these particles back here. And so you maintain some of the nonlinear update, but you're still breaking some of the balance in the model because we don't know if this is an actual solution. But at least the marginal distribution looks right for the Q ice here. And so this brings us to the research question that I'm trying to investigate with this work at NOAA National Severe Storms Laboratory, which is can current convective-scale NWP efforts benefit from localized particle filter approaches such as this? And so the reasons why this may work is because the dynamical processes for this system are quite nonlinear. And also the measurements that we have, which are from satellites and radars, tend to have some nonlinear relationship between the state variables we're trying to estimate. And so there's a lot of suboptimal parts of this problem that make ensemble common filters not work so well on them. Reasons why this may not work is because model errors are still too much of a problem at these scales, which is something you really have to consider, especially for particle filters, where you're assuming that you're sampling from some distribution that has that is correct. And you make and for ensemble common filters, since you're assuming some parametric form for priors, for example, your true state can land somewhere in the tails when you have large model error. Whereas for the particle filter, you're just dealing with a set of states that you have. And also the degrees of freedom may be too large for current ensemble sizes that we use. And so the way I'm going to explore this problem is in this data simulation framework that's used at NOAA National Severe Storms Laboratory. They call it the NSSL Experimental Warn-On Forecast System for Ensembles, or NUSI. And this NUSI system operates within this HURRY system, and this is just a NOAA ensemble that's run experimentally, and it takes boundary conditions in from the GFS ensemble, And it has two domains, one that has a 15-kilometer grid spacing, one that has a 3-kilometer grid spacing. And this newsy ensemble starts from initial conditions from this cycling Hurry system, which is cycled every 1 hour. And it starts from here and then takes boundary conditions in from this 3-kilometer domain and does 15-minute cycling. And it simulates radar, satellite, and surface data every data simulation cycle. And the objective here is to provide a probabilistic prediction for severe weather outbreaks across the United States. And this is all done using only 36 members. We don't have access to something like the K computer at NOAA NSSL. We have to deal with just the limitations of a relatively modest-sized Cray. And so we're only left with 36 members for real-time data simulation system, for our real-time data simulation system there. And the first result I'm going to show is for a tornado outbreak that occurred back in May of last year. And so the region of interest is given by this area here where you have all these red dots. What they are is just tornado reports. And what I did was I just chose one time right here to illustrate what's going on for this situation. And so here, it's a video of composite reflectivity going out to 90 minutes that just shows the evolution of a bunch of convective cells that merge into this linear MCS with time. And these boxes right here are just watches put out by the NOAA Storm Prediction Center. And we also have some weather warning and weather reports that are being shown by these dots right here. And so it's a very complex system in which you start out with scattered convection across the domain and grows up scale into these organized mesoscale convective systems. And so the first thing I'm going to do is just show you what some of the members look like after performing cycling for several hours using the ensemble Kalman filter and the particle filter. And so here I'm just going to show the first 10 members, and what I'm plotting at each of these boxes is the composite reflectivity for each of those members. And on the right here, this is the observed composite reflectivity. And if you look at this, what you see is that each of the members, they look a lot like the observations. So the ensemble Kalman filter does a pretty reasonable job fitting the observations for situations like this. Particle filter looks quite different. So the way I like to distinguish the differences between the particle filter here and the EnKF here is the EnKF looks a lot like the observations, whereas the particle filter looks a lot like the WRF representation of this system, meaning that it contains the same biases that the WRF model has. For example, if you look at these areas, you have very, very high reflectivity. The reason why you have that is because there's a bias in the microphysics scheme that's being used for this application. So if you go back and you run these EnKF members forward a few time steps, these biases show up. And so essentially what you have is this system where you're making updates, and the model is always pulling away from the observations because of some bias. Particle filter, on the other hand, looks quite different because it's essentially selecting the model states that are going to give you that are closest to the observations given by your likelihood calculations. And so if you run the particle filter members forward in time, you get something that looks quite different. It's a smoother evolution from those initial states. And so you have fewer adjustments that are occurring after you perform data simulation with this system. And so the way we're going to verify whether or not we're doing something useful using this nonlinear method is to compare the forecast results with radar velocity winds that are being collected. And so for this particular case, we are lucky because the storm occurred right over a radar. And so we have many forecasts that we can verify using these radar observations. What I'm showing each of these circles right here is just the absolute value of the difference between the VR observations and the ensemble mean. The only thing we can really verify for cases like this with only 36 members is the mean and the variance given by your ensemble, because 36 members is not really large enough to estimate higher order moments of your distribution. And so you can run this forward in time, and you get this nice linear evolution of errors that we can look at. And so if you take all those errors and you average them over several ensemble forecasts and for several data simulation cycles, you get something that looks like this. So the red line is the real-time ensemble data simulation system that's currently being run at NSSL. The blue line is the particle filter. And so we can actually get some improvement using this particle filter, even with 36 members. And so it's a pretty promising result. And the dashed lines right here are just the expected error given by your ensemble. And so I did try to tune the EnKF to provide a larger spread, but it was quite difficult to do that and also maintain the smaller errors. And so that is just for one radar. And it gives us this nice monotonic increase with errors in time, which we want to see. But at the same time, it's not a very vigorous verification since it's just one radar. And so what we did was we took all the other radars in this domain, which is just showing here. So here are all the radars across the United States, and here's our domain. And we took all these radars, and we used them to verify whether we're doing something correctly in this situation. If you look at the results, they're not as neat as before with the single radar example. The reason why is because we have different scan volumes observing different parts of the storm at different times. And so for any given time step of this verification, you could have one radar that's reporting no observations in a region where we have really high errors. And so that's why you have these jumps. So it's not as clean, but you have more information that's being used to verify. And for this case, you still see the particle filter is giving you smaller root mean squared differences to the observations. And so that was just one case. We performed these experiments for 2 additional cases. The first one is just shown right here on the left, which is a case that was very similar to the one that I just showed, in which you have some upscale growth from scattered convective cells across the domain into MCSs. And they're very difficult cases for ensemble common filters because you have these nonlinear interactions between the different storms in your domain that you have to deal with. And on the right, I'm showing another case in which we have one single long-lived tornadic supercell across the domain. And so you can see that from these storm reports right here. You can see these line of red marks. This is just for that one tornado. And so you have 2 very different situations for these different filters. And if you apply the same verification technique which I showed earlier, you can see for the localized particle filter, you can do something that's a little bit more accurate for the forecast for the multi-scale case. For the same reasons why this method did slightly better for the May 24th case I showed earlier. But for the single supercell case, you get comparable performance. And the reason is because this case is just simply too easy, essentially. And so the common filter already does a pretty decent job for this single supercell case. So the results are actually quite intuitive. And so, in summary, a localized particle filter is tested in the NOAA National Severe Storms Laboratory Real-Time Ensemble Prediction System. And so this is a experimental ensemble system that's run every spring for select cases across the United States. And it's used to inform forecasters at the Storm Prediction Center of NOAA. Despite large sampling error caused by these small ensembles and imperfect model, the local particle filter provides comparable results to an EnKF. The reason why I don't say better is because these are only 3 cases, and so I'd rather run more cases before I make any of these conclusions. But so far, the results are quite promising. And using only 36 members, it's also quite encouraging that we can actually do something like this. Other localized particle filter methods will be discussed during this meeting. I'm looking forward to Walter Acevedo's talk, which will look at particle filter EnKF hybrids. There's also some interesting work going on by Roland and his group, and also by Robert and Kunsch with the hybrid EnKF particle filter. And I've seen a presentation recently where they applied this also for a convective-scale problem. So looking forward, the flexibility provided by this particle filter type method allows us to really rethink a lot of the stuff that we're doing right now for designing observing systems. One thing that's not really mentioned during this talk is that you can make any assumptions you want about the distributions you use for your errors. And so we're not just bounded by Gaussian assumptions. And so for the observing system that I use for my current study, we again use Gaussian assumptions for the likelihoods, but we can get away with stuff that's far more appropriate for the observations we're using, especially for observation errors that are known to be bounded. Also, raw observations can be used without rigorous post-processing. There's a lot of nice examples of this, but I like to use an extreme case, a very extreme example, which is for the radar observations that we use, where we have to deal with a Nyquist frequency and the fact that some of the observations are going to be folded over when you exceed a certain velocity. And so for this problem, what you can do with the particle filter is you can actually use a multimodal likelihood function. You don't have to do the velocity unfolding that we do for ensemble common filters. And this is something I'd like to explore some more also in this NSSL framework. And so with that, I'll take any questions that you may have.
Thank you very much.